I want to welcome everyone to another webinar for Energy and Data, and we want to welcome Sunil as a presenter to Energy and Data again. Today we have building an end-to-end solution using machine learning. This webinar is going to be split into parts. Today is going to be a more theoretical side of it and steps and processes, and the next webinar will be in November, where he will actually go over the implementation of the solution and how to do that. For that, you will need some Python knowledge. If you are new to Python, please go back into the Energy and Data website, and you can, in there, access our previous webinar from Alec Walker, Python for Beginners. I'm Annabella Betancourt. I'll be your host today. Before we begin, the model of this webinar is going to be a 40-minute presentation. We're going to follow it with a Q&A session. Sunil Garg, he's the founder and CEO of Data Vedic, an early-stage startup specializing in consulting, big data, analytics, machine learning, and end-to-end data ecosystems for oil and gas industry. Prior to this, he spent over 40 years establishing and growing data management, big data, and analytics business for Schlumberger. Sunil is a sought-after speaker at various industry conferences and also conducts big data, machine learning, and blockchain training for the industry, the government, and academia. He offers a series of classes. A class will be coming up from him in November through AAPG, so be on the lookout for that if you want a more complete view of how to build an end-to-end solution, as the webinar he's presenting today and will continue in November are extracts of that full class. So the material presented today is copyrighted. All the rights belong to the author, and we appreciate that you do not record this presentation. The recordings are made available in the Energy and Data website, as well as SDG Live, as well as the YouTube channel for Energy and Data, so you will have the opportunity to access the information. Energy and Data, if you're not familiarized with it, is a conference that is organized by three societies, AAPG, SDG, and SDE. It's meant to gather professionals from multidisciplinary teams, geoscientists and engineers from small and large oil and gas companies, academia, research, and technology. Our next conference is an online experience, and it's going to be an interactive, immersive, and integrated experience for you, where you can come, ask questions, solve problems, and hear experts share their opinions with regards to where digitalization is going, how technology has advanced, and be able to interact with recognized speakers, peers, people of the same interest, and learn from a large community of people that are contributing to the digitalization of the energy industry. We invite you to participate. The next event will be, again, an online experience, February 23rd through the 24th in 2021, with community building opportunities throughout the whole year. I wanted to run a poll to understand what your domain is. So if you wouldn't mind, I have launched the poll, and if you can start answering it. Sunil, I'm sharing the results with you, but the majority of the people, about 56% are geophysicists, 15% are geologists, 18% petroleum engineers, 5% computer scientists or programmers, and 6% other domains. So at this point, I'm going to stop sharing the results with you, close the poll, and I'll leave you with Sunil. Welcome, Sunil.
Thank you, Annabella. Okay, so we'll go ahead and start. So as Annabella mentioned, right, this is the first in the two-part series where we are going to learn how to build an end-to-end upstream E&P workflow solution using machine learning. And I will talk about the various aspects of building the solution today. In the next part, we are going to actually go through a hands-on exercise where I will go through the Python code in order to build the solution. And that's why Annabella mentioned that you might want to catch up on Python a little bit if you're not aware of it. In any case, it will be a guided session. I will go through every step of the process. Okay. There was a question I just checked the Q&A, and there was a question on whether the recording will be available. Indeed, the recording will be available through Energy in Data website. You can check all our past webinar recordings there as well. So let's go ahead and start. Okay, so these are the points that I want to cover between the two sessions. So what we will cover today is we'll go through what a data science life cycle looks like. When we say machine learning, when we say data science, what does a project actually look like? What are the various steps in that project? Second thing we will look at is how to identify the business pain points. That's typically the start of a data science project, is identifying a pain point or a problem before you can go and build a solution. Then we look at how to define that use case. So take those pain points and how to define a concrete use case in order to build the machine learning based solution. Next step would be to identify and gather the relevant data that is required for that workflow, right? And that is probably the point at which we will stop today. In the next session, we will look at then how to build, train, and test the machine learning model using Python. How to validate that model, right? Both from a data science perspective as well as from a user's perspective, right? And then how to build a complete solution around it and operationalize it so that the end users can use it. So those last 3 steps, I would say we will cover in the next part of the session. Okay, so just first looking at what does a data science life cycle look like. Okay, so you can see that it's kind of an iterative loop, and where we start with the business understanding. That's the first step in the process. From there, we will go and look at the data. We will go and build the machine learning model. We will validate and test that machine learning model, and then we will put it into operation so that the end users can use the solution. Various steps that are required. So you may observe that I keep calling it a machine learning based solution and not just a machine learning model, because you can see that building the model is actually just one step in that process. Okay? There are other steps which go around building the entire solution. Right? So the model is just one part of that process. So we start with business understanding. So first part of business understanding is essentially looking at what does a data science team actually look like. Okay? I put some stakeholders on this slide, which is how typical data science solutions team is composed. Not a data scientist team, not a machine learning model building team, but a data science solutions team which can come up with a full end user solution. The critical part of that team is, of course, the business stakeholder and the domain expert. And there may not be two distinct roles. Two distinct people playing that role. There may be same person playing the role, or maybe there may be different people. And that's true for every one of these roles, right? In a very small project, you may have, in fact, 1 or 2 people who may be playing all the roles. Okay? So business stakeholder and domain expert are the 2 key people who are primarily responsible for defining the problem and defining the value that you will gain out of the solution. Okay? So that is where the actual project starts. And then the remaining people that you see in that solutions team, which is, let's say, a data scientist, a data engineer, or a data management person, software developers, software testers, these guys are all involved in building the solution based on the information that they gain from the business stakeholder and the domain expert. Ideally, in any data science team, a domain expert is an integral part of the team which is building the solution, so that it's not just one-time feedback. It's not just the definition of the problem, but they're intimately involved in selecting the data. They're also involved in giving the feedback while the solution is being built, and for validating the solution from a domain perspective. Okay? And then the last part, which is what, when we do the second session, we will cover that part, which is the operational support of that. What happens after you have, let's say, built the model and you try to operationalize it, and what happens in the future, right? What does the life cycle look like once the first version of the solution has been released? So that part we'll cover in the second session. So that's a typical data science solutions team. If you see any roles missing, I would be more than happy to see your feedback. Please put that in the Q&A session or in the chat box, right? That's basically your feedback to see any roles missing. There is one critical role that I actually left out of this, and I wanted to see if people would detect that, right? And we can talk about it as we go through it. So next part is understanding the business pain points, right? This is where everything starts from, right? If there is no understanding of the business pain points, then you may not be able to come up with a good solution, right? You don't want to fit a solution to the problem. You want to understand the business pain points, formulate the problem, and then you want to put together a solution which will solve that problem. So there are many business pain points. So I will take some at very high level, right? What do we face today? A low oil price environment which has persisted for almost last 5 years, right, and has been further, deteriorating due to the COVID-19 and the oil price, right? So optimization of the costs is a very, let's say, critical focus in any oil and gas company and any oil field services company as well. Okay? So optimization of the cost along with enhancing the operational efficiency allows you to essentially do the same operation in lesser amount of time with the fewer resources that are there today. Okay? As we look at lesser resources today, safety becomes a critical issue because typically lesser the number of people, there is a high probability of safety incidents happening. There is a high probability of accidents happening. Right? So improvement of the safety and minimizing incidents is another focus from a business perspective. Next focus is on automation because typically manual operations are time consuming, right? They're also dependent on a lot of people and there are a lot more potential to make mistakes when you have manual operations. Right? So automation can help in solving some of these issues, right? And making sure that, at least the repetitive operations and sometimes even the mundane operations can be automated so that you can get better business results out of this. Another business pain point is lack of repeatability, which means when we put together some of these solutions today, can I repeat that solution for similar data set or maybe a different set of data set, maybe in a different area, a different field, a different basin. Right? If there is a lack of repeatability, essentially the solution is not good, right? Then you don't have the reliability to say, well, I can solve this problem consistently and in a repeatable manner. Another business pain point, and this is a data science pain point as well, but another business pain point is the questionable data quality or poor data quality. Right? Very often we see when we are trying to work with the data, you will see duplicate data, you will see many different versions of the data which don't match with each other. You will also see sometimes incomplete data, which means some critical values are missing, or you can see inconsistent data stored in different systems. They don't agree with each other, they are inconsistent. Right? You will also see sometimes data which does not agree with science. Essentially, it is violating the science, which means there may have been either a typing mistake or a reporting mistake. Okay? So all of those are huge pains because anything you try to do from data and try to learn from data, the results can get compromised if the data quality is not reliable. Okay? Another one that we see typically as a business pain point is bias on interpretation. We have also seen, how multiple interpreters or multiple geoscientists in the same oil company are interpreting the data simply because there is a lack of reliability. Okay? That can introduce too much bias on the interpretations themselves and also unreliable results because now you have multiple results. Okay? And the last part, which is too many technologies but no real integrated solution. There is a lot of technology out there today. Not only in the areas of when we say machine learning and big data, but let's say for data management, for data quality management, lots of technologies and there are lots of technology components, okay? Lots of platforms out there as well. Right? What does an end user use? Right? Let's say if you are a geoscientist, a production engineer, a drilling engineer, what you really need is a solution. Right? You don't need those technology components. You need a solution that works for you, that you can reliably use without worrying about the technology components that are sitting behind the solution. And there are lots of technologies out there, but in general, there is a lack of proven working solutions. Okay? And that becomes a business pain point because in order to let's say, try to solve that problem and get a sanction for the budget, all that, right? That becomes a hurdle. If you cannot prove that, yes, there is a good chance and good probability of getting a solution. Okay. The next part that I wanted to take on the business understanding topic is the data science pain points, right? So let's say the pain points have been defined, you have defined a problem. What is it that typically the data science team faces? Okay. The first and the foremost part in that is that in any data science team and in a data science solutions team, right, 90% of the time is spent in data ingestion and data wrangling. You may remember when I started the webinar, I said, okay, I'm not going to focus just on machine learning. I'm going to focus on the entire solution, not just on machine learning model. And if time is getting spent, and if 90% of the time is getting spent in data ingestion and data wrangling, that means the amount of time that is actually allocated and is being spent in building the machine learning model itself is greatly reduced. Okay, so you don't have sufficient time left essentially to build that model. And that's a pretty big data science pain point everywhere. The statistics vary. You know, when I started doing data science, let's say 5 years ago in 2014, in fact, right, pretty much people said, well, 60 to 70%, right? And increasingly we have seen that it's really not 60 to 70 from actual projects. My experience has been 90% of the time. The next thing that data science team faces, which I mentioned in the business pain point as well, is the questionable data quality, right? And that really hurts, because if the data quality is poor, then the model that you are going to build is going to learn from that same data and may give poor results as well, right? So essentially garbage in, garbage out. Okay. The next part, which typically data science teams face, is the machine learning models themselves, right? They are seen as black boxes, which means people are unable to understand how the model is predicting the results. Okay, and that becomes a pretty big question mark on the reliability of the model. People want to believe in the model, right? But if they are seen as complete black boxes, they will not be able to rely on the results of the model. So it is critical for any data science solution team is to build enough, I would say, proof points as well as, let's say, dashboards, statistics, in order to make sure that the domain experts and the end users can understand what the model is doing and what its performance is. Okay. Next one on data science pain points is the lack of reproducibility. And this is something that is widespread in the data science area, that more and more there is a demand for saying that if you built a model, somebody else should be able to reproduce the similar results and the similar outcomes, maybe with the same data set, but also sometimes with different data sets. Right? The outcome should be proven. Right? And the lack of reproducibility really hurts the whole data science team, because people will not be able to rely upon that model to repeatedly give the results. Okay, the next part is the poor rate of conversion of machine learning models into end user solutions. And what that means is there are lots of prototypes and pilots, right, on the machine learning side. And typically the purpose of a prototype or a pilot is to build a quick solution, is to build a quick model and say, yes, there is a potential to solve this problem using machine learning, right? A prototype or a pilot is typically not geared towards being the end user solution. And historically what we have seen is that there's very few out of these pilots go out and get converted into end user solutions. And the reason can be many. It's not just purely technical reasons. Sometimes there is a lack of understanding. Sometimes there is a misalignment of expectations. As an example, I've been in a project where the stakeholder thought that during the pilot we are building a complete solution, and their assumption was that at the end of those 8 weeks, they are basically able to use the solution and give it in the hands of the end user, right? Here, there is a misalignment of the expectation. Okay, so there are many reasons for that, not just the technical reasons. And then the last main point, which I mentioned on the business side as well, too many technologies, which means I have lots of technology components, lots of frameworks, a ton of machine learning libraries out there, right? But there's a real lack of integrated solutions, and an integrated solution is really required in order to use the solution, in order for the solution to be usable by the end user. Okay, so let's go to the next step in that, and this is still, I'm still on the first part of it, which is the business understanding. So next step, we have understood the pain point, right? We have looked at, pain points from both business perspective as well as data science perspective. The next step is essentially a launch into the project, which is defining the use case, right? So based on the pain points, you say, okay, what do I want to solve, right? And elaborate that problem essentially. Right, so I want to understand first what is the current process. Let's say if I'm trying to solve a problem, if there is a solution that exists today, is there a process around it? What is it? What is used currently to solve that problem? What does the outcome look like? What does the solution look like? What do the end users get as the solution today? What is the accuracy of that solution? Is there any question marks on the accuracy of the solution? Do the users think it is reliable, right, or not? Right, and then if there is a need to build a new solution or not, right? That's typically a question to be answered at this stage, because sometimes as you elaborate this, you say, well, probably I have a good enough solution. May not be the best solution, but maybe I have a good enough solution for this market need, right? You can stop at this stage if that is the outcome. Okay? But if not, then you go further and say, okay, if I am going to use data science to build a solution, what is it that is expected out of it? What is the success criteria? What is the accuracy of the model that is expected? How will the model be tested, or how will the solution be tested? So, and then, you also discuss at that point a little bit around how the solution will look like and what will be the sustainability of that solution, right? So that's kind of, I would say, the discussion that happens while defining the use case. So that's essentially the use case that we will deal with. So here is an example of the use case. And like I said, this will be in the second part of this session, which is on November 19th, right? This is the use case we will take, where we are going to predict a gamma ray log based on the gamma ray logs of the surrounding wells. Okay? Essentially, we are synthesizing a gamma ray log based on the existing data. Why are we doing this, and what is the motivation for this? Right? So typically the gamma ray log gives you a very good idea of the lithology of the earth, right? So it can tell you very quickly, right, where is the reservoir rock, such as the sandstone or the limestone, right? And in US, of course, there is a lot of shale drilling, and shales are typically more radioactive, right? So that looking at the gamma ray log can tell you very quickly where those shales are, right? And that will help you in correlating the markers. That will help you in basically looking at your stratigraphy. Right? If we are able to do that, what's the benefit that it gives? And this is the kind of value you want to put, right? So I'm giving you an example in this use case, but this is essentially what you want to put during your use case definition. You want to define the use case and you say, why are you doing the use case? What is the value that I'm going to get out of it, right? So if I have a synthetic gamma ray before even I started drilling my well, it gives me a very good idea of the rock type and the formations that when I drill that I'm likely to encounter. If I know that better, right, that's an input into my drilling plan. That's what decides, what kind of bit will I choose, what is the rate of penetration that I can get, what kind of weight on bit will I use, what kind of mud weight I will use. So those kind of things, all your drilling planning parameters can be improved, once you have a better idea of the rock type and the formations that you are going to encounter. So essentially, you can increase the efficiency of drilling operation even during the planning stage. This is still in the planning stage. Of course, you will do the similar things once the drilling starts. But at the planning stage, a synthetic gamma ray log can be very useful in order to improve your plan. So that's essentially an example of a value that we would typically put together. Once we do that, then we go to the next step, right? So you have defined the pain point. You have said, okay, this is the problem I want to solve. You've defined that use case and you have put together some value out of that use case in order to put it in front of the stakeholder. Let's say you got the project approved. Let's say the stakeholder says, yes, I'm convinced about the value of this. Let's go to the next step. So what is the next step? Next step is to see if data is available, right? If data is available in the right shape, is it accessible? Sometimes it is available, but you may not have the rights to the data. Right? So is it accessible? Is it of the right quality? So all of those issues we will look at in this phase, which is the data phase. So first part on that is, of course, identifying and collecting the data, right? We want to look at what is the data that I require in order to solve that particular problem. Based on the use case that we have just discussed, we will of course need, let's say the well locations, the gamma ray logs, potentially the trajectories if you want to deal with horizontal wells or the deviated wells. In this case, we will probably take only the vertical wells so that we can avoid that. But otherwise, you would have needed the trajectories. You need your elevation references. So those are different types of data types that you can identify when you define the problem. Right? The next part is looking at, okay, where do I get this data from, right? So I've defined the data types. Is that data sitting in a database on, let's say, in a particular company? Is that sitting in files? Or maybe in case of streaming data, do I have access to the sensors from which the data will stream in? Sometimes, the data may be coming from another application or another application store, right? So do I have access to that application store? Or in some cases, people do research on the public data, right? So do I need to go to a data vendor and get the data from there? Right? So those are all relevant data sources. At this stage, your only goal is to identify where the data sits, and sometimes you may identify multiple places from where you can get the data. Right? You don't know which one is more accessible, but at this stage, it's more important to identify the sources where potentially you can get the data. And then apart from collecting the data that is already sitting into one of the systems, you can also get some derived data or some processed data, right? So you can say, well, after getting this data, maybe I want to get either some aggregated data, maybe some filtered data, maybe I have a large volume of data and all of that is not useful. I may want to do some interpolation in case there is missing data, maybe some depth correlations and depth shifts have to be done for the log code data, let's say. Right, so any of that, that's essentially your derived data. Right? So apart from the raw data that you can get out of these sources, right, you may have some processing and some processed data resulting out of that data. Right? So all of that is valid data source depending on your use case. So that's the first part of it, is to identify where I can get the data and collect the data. Okay, so some aspects or some issues that you need to pay attention to while doing that is, if you have multiple sources of data, is there a way to know which one is the preferred source, right? Especially, if it's exactly the same data piece or the data type sitting in multiple places, right? So you need to know which one has better reliability so you can get hold of that. Of course, sometimes the better reliable system may not be accessible, in which case you take your second preference. But at least you need to know what is the quality or what is the type of data that you are trying to get. Next part is, if you got the data in the form of files, let's say, right, which is very common actually, right? CSV files, LAS files for the logs, SegWi files for the seismic data, UQA files for seismic navigation. So, right, you get data in all sorts of forms. So if you get the data in the form of files, do you have the parser to parse the data? Right? If you cannot get the data out of those files, essentially you cannot really run your data science project. That means you have some additional time added to your project in order to get the data. Okay. If you can get the data out, the second thing to pay attention to is, let's say if I take CSV, and that could be any kind of, really not just CSV file, but any kind of, let's say, ASCII file, which may be delimited maybe by a delimiter, or let's say a formatted file, right? Maybe a fixed width file. Right? So in that cases, you need to be aware of what your delimiters are. Is it a comma separated file? Is it a tab separated file? Right? Depending on the file, you can parse it. If the data is sitting in a database, what are the database protocols? What that means is, how do I get authenticated and get access to the database? What language do I need to use? Is it a relational database? Is it a NoSQL database, which is, use of NoSQL database is rising today. And there are many different types of NoSQL databases. So each may have its own language to query the data and extract the data. So that's all comes in, understanding the database protocols so that you are ready to extract the data. Apart from the data, you may also be reading some metadata about that data. For example, just take a very simple case. Since in this case, the one that we are going to use, we are going to use the gamma ray logs. And let's say we start with the LAS files. You don't want to read only your ASCII section, which is where your gamma ray log values are sitting, but you also want to read your log headers. And that log header essentially serves as a metadata for that ASCII section, right? And you may have other metadata in terms of, what's the source of that data, what kind of, let's say, processing it has gone through. So sometimes that kind of information also sits in the metadata. Okay. In case there is data redundancy, right? Is that useful for you? Sometimes it can be useful actually, especially if you have missing pieces of data in one system, which could be augmented using, let's say, data from another system. Right? The flip side of that is if you have duplicate data where let's say large amount of the data is similar but a small pieces differ, which one do you take, right? So there is an advantage and disadvantage of that. And the last part in that is taking the data from the data source, right, which is what we looked at the data source in the previous slide, and then looked at the various mechanisms in order to extract the data, putting that data together in a place where you can build your machine learning model ultimately, right? And that is an opportunity essentially to build your data store or data lake. And some of the characteristics that you will look from such a data store or data lake would be not only able to store the data, but being able to connect all the data pieces together. This is critically important if data is coming from multiple sources where you may or may not have the same, let's say, identifiers which can connect the data. So you may have some work to do essentially in connecting the data. This is also the environment that you will typically look at to say, because I'm going to run machine learning in this environment, I should have sufficient memory, sufficient compute capacity, which means sufficient CPU, right? And I should have sufficient storage space in order to store the data as well. I may be producing various versions of the data while doing the machine learning, right? So all those become important. And nowadays, especially last 4 or 5 years, you can see that there is a lot of cluster computing that happens. And cluster computing basically by using commodity machines rather than by using, let's say, supercomputers or the mainframe computers, which is what we would use in the past. So essentially distributed computing is happening more and more for something like this. Okay, so next step in looking at the data is the pre-processing of the data. So I've still not reached the machine learning stage, right? I want to get my data ready for machine learning. So I have the data, I have gleaned the data out. Next step is looking at the pre-processing the data, and that is what I call as getting the data analytics ready, right? So there will be many steps. There could be many steps in pre-processing. Improving the data quality, right, is a critical step, right? Typically, you are looking at, is the data valid? Are there any incorrect values? Maybe the data is out of range in some cases, which means it's incorrect data again. All the data pieces that I need, are they complete? Very often you will see coordinate systems missing. Sometimes you don't have elevation references available, which means your depths could be completely wrong. Right? So those are different sources of, let's say, different data quality areas that you want to deal with. Next part is looking at the consistency of the data around their frame of references. Okay, so which means the units in which the data is expressed, the coordinates in which the data is expressed, time zones, date formats. And this is also again critically important if data is coming from multiple sources. You really don't want to feed the data into your machine learning model algorithm where it is inconsistent. So your frame of reference has to be consistent. Another issue that comes up in data processing, pre-processing very often is the missing values, right? So if I have some data missing, for example, in this case, when we take the last files, if I have null values or absent values for the gamma ray, what do I do with those? Should I fill them up with some value, maybe mean, median, something? Or should I leave them, maybe skip that section in the training? It all depends on the use case. So essentially you have to have a strategy depending on the use case to handle that missing data, right? Also, you need to look at consistency of the data and see if there are some outliers. The outliers are typically the data that will not fit the trend or that may not fit what you are trying to do, right? So again, outliers are dependent on use cases. It should be away in data science studies that outliers are separated out. However, you will find that sometimes the entire knowledge is hidden in the outliers. At least I've been in the middle of projects where the only goal was to in fact say, what do the outliers tell me? Why are these outliers there, right? So sometimes knowledge is hidden in that. So even though you are separating it out, you definitely don't want to throw those away. You may want to get more insights from those. Okay. Another common processing technique is to get some derived data out of, let's say, aggregations, which means, let's say, you're calculating mean, median, standard deviation, any kind of statistics around that data. Okay, depending on your use case. Sometimes you will normalize the data as well, which means you're kind of getting the ranges of the data, especially for the numerical data. You're kind of getting their ranges in a similar range, basically. This is critically important for some algorithms like neural networks, where you don't want to just feed the data with different ranges. If one data value is much larger in terms of its scale compared to another data value, that can impact your machine learning model. So definitely you want to look at a good normalization strategy. Another one that is typically done more for the categorical variables is something like hot encoding, which is essentially a data science technique to, the way I say it is, flatten the data or pivot the data. Okay, which is taking, let's say, if you have yes no kind of column, right? Maybe you split it into two columns, one which says yes is equal to 1, other which says no is equal to 1. It's just a very simple example of that, right? That's what a one hot encoding would do. Before you build the machine learning model, you also look at what is called as feature or dimensionality reduction. And the primary reason to look at that is the larger the number of features, the more complex machinery, the more memory, more compute, right, more storage you will need in order to train the model, and more time it will take to train the model. Okay? At the end, your model will also be more complex, and it will be more black box if you have more features. So there are many motivations for reducing the number of features. So you want to take only the relevant features. More so if two features exactly correlate with each other, right? If there are two input features which look very similar in terms of their trend, they're probably going to impact the result in the same way. So you may want to skip one of them. Yep. So that's feature reduction or dimensionality reduction. Noise is pretty big pain, especially in this, if you are getting a lot of high frequency data, right? If you don't remove the noise, that can impact your results, because you may end up capturing the trend of the noise rather than capturing the trend of your actual signal or the actual data. So noise reduction is another part of data pre-processing. Sometimes you may need to smooth the data. This is again very relevant when you have high frequency data, because either you may not be able to handle that higher frequency, or handling, let's say, very granular data, right, may impact the results or may impact what you are trying to do. Okay. Other things like unbalanced data, there are many such things basically that you will do, right? And it all depends on the kind of pre-processing, depends on the kind of use case that you are building. It's important to understand the different techniques that are available so that you can gauge and decide which ones to apply. So that's again part of the data step in that. So we have identified the data, collected the data, let's say stored it into a data lake, run the pre-processing. And by the way, pre-processing does not need to be run only in the data lake. Sometimes people do it on the original files or when the data is being ingested. It all depends on how much speed you can get it in, right? And what is the stage where it is more important. For example, sometimes after ingesting the data, it may not be possible to run some corrections, in which case you may want to run it before you put it into the. Okay, in this case, the example that we will take next time will be, we will take well headers for vertical wells only. In this case, 6 wells I think we have, yes, in the training set. We will use 5 wells for the training, and we will use 1 well for the blind test. Okay, so we will have LAS files for the gamma ray logs, well headers in a flat file, a simple flat file, and that's where we will start from. Okay, next part, and this is where we are going to stop in this webinar, is the actual data analytics, right? So when we say machine learning model building, what do we mean by that, right? So it's essentially, by doing data analytics, you are trying to capture the patterns in the data, and you are trying to capture it in a form in which you can make some decisions on that, right? So it's essentially trying to glean out knowledge from the data in a form that you can train, let's say, algorithms or machines to interpret that, make some decisions, and essentially reach towards automation. There are many terminologies that are used, AI, machine learning, deep learning. I would not worry too much about it. This is a very simple definition, and I know there are many definitions out there, right? AI, very simply, you can say machines making decisions, whether they're trained, untrained by human beings, different matter. Machine learning, typically, your goal is for the machine to make the decisions without doing explicit programming. That does not mean no programming. That means the machine learns based on its experience, basically. So you need to give something for the machine to learn, but you may not have programmed every step of that explicitly, right? And then on the deep learning side is specifically the field where you typically use artificial neural networks, and the decision and the data is pretty complex in this case. Okay, so it's a specialized form of, you can say, machine learning. And I would be more than happy to discuss this subject in detail at some point of time. And if you have feedback, I would be more than happy to take that feedback as well. Okay, last part on that. So these are just very quick high-level overview of what different machine learning algorithms look like. Commonly used ones, supervised machine learning models, which means you have some inputs and you have some output data. And essentially what you are trying to do is to reverse engineer from that basically, right? So you're trying to reverse engineer, let's say in a very simple form, an equation which will calculate that output based on your inputs. Okay, you will hear terms like regression and classification. Those are types of models that can be built using supervised machine learning. Okay. Unsupervised machine learning is typically used when you do not have output data or you do not know what you are looking for. You sometimes are trying to just discover. You have a bunch of data, you're trying to discover and study the data and trying to maybe discover the groupings in the data. Okay, so that's when unsupervised machine learning is used. Typically, in most cases, unsupervised machine learning is a precursor or a step towards the supervised machine. Okay? It's basically used to understand the data and the relationships before you can ultimately build a supervised model. Right? And then there is reinforcement learning, where what you are trying to do is you are trying to use trial and error method, essentially to see what outcome will come out of it, and you define what is a successful outcome and what is a failure outcome. And based on the various steps that are taken to reach that outcome, you reward the system or penalize the system. This is how the machines will learn basically in order to solve a problem. A good example of that would be, let's say you are trying to teach chess or Go or one of the complex games, right, where there are a series of steps, right? You are trying to teach the machine the various ways of playing those games. There is no way to teach the machine every single step that you can take towards a possible successful outcome. That is why they learn by playing those games, right? So that is where reinforcement learning is. Okay, this is where we will stop today. I will open this to questions now. We are just about, so we have about 10-15 minutes for the questions. So let's go ahead and go through the questions, right? And then after the question, we'll just wrap up by saying where we will start in the next session.
Thank you, Sunil. Okay, so the first question was, can you give a prorated percentage of time allocation of how long each component of machine learning life cycle is expected to spend?
Sure, I will give you some from my experience, okay? And different people probably have different experiences, but probably some data which will fit. So till the time, so if I start from the data source, right, up till the time I have the machine learning model. Okay, I will skip the last part of it, which is converting that into a solution. But till the part where machine learning model is built and validated, I would say the machine learning model step is probably 10 to 15%, and rest, your 85 to 90% time is pretty much spent in getting everything else done, which is your identifying data, collecting data, pre-processing the data, getting the data into a data lake, ingesting it, all of that basically. So if you have a data management system where all the data is properly collected together, right, and is in a good shape in terms of quality, you get a big leg up in this process. Okay, so if you can rely on a good quality data management system, then you can get a good leg up on the machine learning model itself.
Please explain in detail the role of business stakeholder. Is a geophysicist fit for that role who did not have an MBA or a business certification?
Okay, so there are two roles, by the way, right? So I will come to both of them because I think there may be some overlap between the two. First one is the business stakeholder is essentially the person you are looking up to get the budget. Okay, so there has to be somebody on the business side to say, yes, this makes sense and I can approve the budget for it and I can sell the value to the management. Okay, so yes, a geophysicist can definitely fit the role provided you understand what is going to be the value of that solution, and maybe if you have approving authority for the budget. If you do not have approving authority for the budget, a geophysicist may fit better in the domain expert role. Remember, I had another role under that, right? The domain expert's role is to get that preparatory work done to put it in front of the business stakeholder. Right? They are the ones who are saying, okay, this problem can be potentially solved using machine learning, and they are also the ones who are coordinating, let's say, with ultimately with the data science team, explaining to them what the problem looks like, what potentially the data what is the data that could be used to solve that problem, and we'll also work with the team in order to validate that solution once it is.
All right, the next one. Interpretation bias is in geoscience. Based on experience on working in a field, the interpretation can vary. Based on the uncertainty in the data, there is bound to have interpretation bias. This is my experience. So I guess it was just a comment, not a question. How can the drilling engineer use gamma ray to come up with mud weight?
Okay, that's a good question. In fact, gamma ray is not the only way to come up with the mud weight, right? That will be one input to come up with the mud weight, because remember what you are using gamma ray for, right? You are trying to figure out what rock you are going to encounter, and based on that, you will plan your drilling operation. Right? And that's one input. That's basically your fixed input. That's the input that is not in your control, essentially, right? So because that's the earth, basically, that's what exists. So that will be one of the inputs that will go into planning that, right? Including with, so you will need to do your other inputs, which is, what kind of trajectory do I want? What are going to be my section diameters? And once you're done with all of that, then only you will be able to come up. Okay, next question.
Next question. In case of fluvial clastic reservoir and much heterogeneous in nature, then which
so I think I understand
who ML will help to predict?
Yeah, I think what the question means is that can ML still help, right? If the data is very heterogeneous in nature, can the ML still help, right? So just remember
I think it's a contrast. Like if you have a classic reservoir, yeah, or it gets a heterogeneous reservoir, in which case you can implement machine learning.
Yes. So just remember the basic principle of that, right? The machine is trying to learn from the data. The algorithm is trying to learn from the data and is trying to figure out the trends in the data, right? If the data is very, very heterogeneous and does not show any trend, I would say the machine learning will have hard time there, basically, right? Also remember that typically, and this is something that I will show you when I show the actual, when we cover the actual workflow next time, when we build the machine learning model, that domain is very critical to some of these. Okay, these are not, I mean, especially in oil and gas, you will be hard pressed to find a solution which works purely on data science and is very successful. And the reason I say that is there are many aspects of this, including uncertainty, okay, which you cannot just capture based on purely the statistical part of it. You need to have the domain knowledge in order to deal with something. Right? So in case of, again, heterogeneity, unless there is some consistency and some trends that it can find, machine learning may have a hard time in figuring out anything.
So what is the difference between remove outliers and noise reduction?
Good question again. So outliers may not be noise. Okay, noise really, when I say noise reduction, that means really something that is happening, for example, because you are trying to physically capture the data from a machinery, right? There is an inherent, sometimes noise in there. Outlier, on the other hand, so a common example I would give you, if I am doing, for example, I've, in the previous webinar, I showed formation tops prediction, right? And in that, if there is a fault that appears in your data, or if there is an unconformity that appears in your data, that may look like an outlier to start, right? Simply because it is not conforming with the rest of your, let's say, the formation. Okay, that doesn't mean that is noise, right? So that's the primary distinction is outlier may all be valid data. You don't know in the beginning, but it may all be valid data. And that is why sometimes I say the entire knowledge is hidden in the outliers. Okay. On the other hand, noise is really data that is not valid. Basically, it's the data that is supposed to be thrown. And people do have struggle, by the way, in separating out the outlier and the real noise. Okay. So that is one of the key challenges in data science, is to cleanly separate that.
Okay, the next question is, how training data incorporate the geological variability, meaning how to incorporate geological trends.
It will incorporate as much as you feed in. Taking the previous example again, if I built a model based on, let's say, the logs and trying to predict the formation tops, and you never told the model what a fault is, it will incorporate it, but it will not be able to tell you that it is. It will probably, the model will probably point out something unusual is happening, but it may not be able to say, this is a fault. On the other hand, if you teach the model that here is how a fault would look like, what is the statistical way of looking at the fault, it may be probably able to do that. Okay, so it will basically incorporate the variability as much as you feed it. You have to teach the model.
Okay, how to incorporate uncertainty in machine learning?
So uncertainty is typically related to, the way you are going to predict. For example, right, there are many ways of, let's say outcomes, right, which is something that we didn't talk about today, because that's after building the machine learning model, we will look at how to measure the performance of the model and what will the outcome look like, right? The outcome may be one answer to say, here is what I think the prediction would be, or the outcome may be a probability, right? So you can incorporate the uncertainty by giving a probabilistic answer to say, here is the probability of this answer, and here is another probability of a different answer. Okay, so you can build all of that into the model, right, depending on the type of outcome that you need.
All right, so we're almost at the top of the hour. I want to thank you, Sunil, for this webinar. I want to remind everybody that the continuation of this webinar, where you actually will see how to implement the solution, will be in November. Also, we have a series of webinars planned, and the next one for next month, October 26th, will be machine learning implementations in oil and gas, success stories and challenges ahead. We want to also invite you to go back into the Energy and Data webpage that you used to register for this webinar to watch the Python for Beginner webinar if you have not done so, as it will be a requirement to continue the second part of the end-to-end solutions implementation from Sunil in November. We also want to remind you that our Energy in Data event has changed to an online experience, and it will be held in February 23rd and 24th. I want to thank you, Sunil, for this excellent webinar. Looking forward to the continuation of it. And I want to thank everybody for attending this webinar. Have a nice day.
Thank you, Annabella, and thanks everybody for attending it. Here is my contact information. And to answer that last question that was there on the screen, all the webinar recordings that are being conducted as part of this series, they're all on the Energy in Data website. It's right, you go to the website, you look at webinars, all the recordings are right there. And say this recording will appear at the same places. Okay.
Excellent. Thank you so much.
Thank you.
Bye.
Bye.